Hello and welcome to this presentation of the I3C peripheral embedded in the STM32H5. This applies to STM32H5 6X and 573 and STM32H503. This presentation starts with a quick overview, key features, MIPI specification support, product-dependent features. It's followed by describing the following items: I3C peripheral state and its programming sequence, I3C MIPI supported Common Command Codes or CCC, a few examples which illustrate I3C bus transfers and register setting, a few examples clarifying the I3C FIFOs management, the list of interrupts and underlying functional events, and wake up from stop. I3C defines the electrical connection between the chips to be a two-wire shared or multi-drop serial data bus, one wire SCL being used as a clock to define the sampling times, the other wire SDA being used as a data line. The standard defines a signaling protocol in which multiple chips can control communication and thereby act as the bus controller. The I3C specification uses the same electrical connections as and allows some backward compatibility with the I2C bus. In the upper figure, a host controller is connected to both I2C and I3C devices. The primary controller is in charge of the I3C bus initialization, while a secondary master initially acts as a slave, but can also accept mastership from any current master. Note that an I2C device must use a separate signal to generate an interrupt request to the host controller, while I3C supports a native in-band interrupt mechanism known as IBI. The bottom figure represents an I3C typical communication. First, the master issues a start and then broadcasts address 7E followed by RNW20. Then the master turns on a pull-up resistor and goes to open drain while all slaves act by pulling the SDA line low. In the second part of the transaction, the master then issues a repeated start, then the address of the slave 2B it wants to read, followed by RNW21. The master then turns on a pull-up resistor and goes to open drain, allowing the slave to acknowledge by pulling the SDA line low. At this point, the master continues to toggle the SCL line and release the SDA line, allowing the slave to drive SDA to send 1 byte of data for A followed by T. T equals 1 informs the master that there's additional data, whereas T equals 0 signals the end. Here there's additional data, so the slave drives SDA high until SCL goes high, at which time it releases SDA. In addition to IBI, I3C contributes to reduce the pin count by supporting an in-band reset and in-band power modes control. The I3C protocol supports a hot join mechanism to allow slaves to join the I3C bus after it's already configured. The error detection and recovery methods are provided in order to avoid fatal conditions when errors occur. The I3C unit present in STM32H5 is compatible with I3C revision 1.1 specification. Only single data rate or SDR mode is supported. This slide and the following one lists the I3C peripheral features. The I3C peripheral can be configured to be an SDR-only primary controller, an SDR-only secondary controller, or an SDR-only target. The following timings are configurable: SCL high and low times, SCL stall time and bus-free condition when operating as a controller, SDA hold time and bus available and idle condition time when operating as a slave. To facilitate the software management, the I3C peripheral implements the following queues: data transfer queues, transmit FIFO for data bytes/words to be transmitted on the I3C bus, and receive FIFO for data bytes/words received from I3C bus. A control FIFO called C-FIFO for control words to be sent on the I3C bus, an optional status FIFO called S-FIFO for status words received from the I3C bus. For each FIFO, an additional DMA mode can offload the Cortex M33 core by moving data to and from buffers allocated in memory. The target device supports the following requests: in-band interrupts with up to 4 byte payload, and bus control and hot joint requests. The I3C peripheral, when acting as a controller, supports up to 4 simultaneous requests initiated by target devices. The software manages messages at the I3C frame level. Management is based on individual programmable events, including bus error detection and recovery. The I3C peripheral is implemented with several clock domains: APB clock for register access, I3C kernel clock, and I3C bus clock. The I3C hardware automatically switches from and to SDA push-pull and open drain modes. Push-pull is used when communication is unidirectional and there's no chance of another device communicating at the same time. The allocated GPIOs for SCL and SDA must be configured with the alternate function and no pull. The I3C peripheral can work in autonomous mode, enabling transfers during low-power modes with DMA. I3C can wake up the system from low-power modes on the following conditions: acknowledged target request completion and DMA-based triggered frame completion when operating as a controller, missed start detection and reset pattern detection when operating as a target device. The STM32H5 includes 2 I3C peripheral instances so that the device can support target operation on one I3C peripheral and operate as a controller on the other I3C peripheral. The figure represents this possible configuration. The I3C peripheral does not support native hardware triggers because the ones implemented in the DMA controller can be used instead. When the microcontroller is in stop mode, the I3C can work in autonomous mode and cause the wake-up of the CPU. In this case, the system stop mode voltage scale 3 mode shall be chosen. The STM32H5 and STM32H5 have a unique I3C peripheral instance. The figure represents the I3C peripheral configured as a controller in the microcontroller. The features of the I3C peripheral are identical to the ones in the STM32H5 This table indicates which features described in the I3C MIPI specification revision 1.1 are actually implemented in the STM32H5 I3C peripheral unit. In brief, the I3C peripheral supports all the mandatory features of the MIPI specification version 1.1. This includes single data rate message, dynamic address assignment, grouped addressing, error detection and recovery, IBI, secondary controller, hot join, target reset, asynchronous timing control mode 0. Synchronous and asynchronous timestamping improves the accuracy of applications that fuse signals from various peripherals. When operating as a controller, the following features are also supported: I2C static addresses, I2C message handling, and device-to-device tunneling. The following optional features are not implemented: high data rate signaling, synchronous and asynchronous timing control modes 1, 2, and 3, multi-lane operation, and device early termination monitoring. The list of supported CCC commands is detailed in the next slides. The I3C peripheral is implemented with several clock domains: the SCL bus signals for the I3C bus interface, the I3C CLK kernel clock for the I3C protocol management, data and control serialization and deserialization, controller and target finite state machines, the APB clock for the APB interface, DMA interface, events, and interrupt generation. APB clock and kernel clocks are driven from independently programmed clock sources via the RCC, reset and clock controller block. The I3C kernel clock and the APB clock frequencies are to be set at a minimum value versus the intended operating SCL bus clock frequency. Refer to the reference manual for the list of the clock requirements and constraints. To save dynamic power consumption, the I3C peripheral hardware automatically manages its own clock gating and generates a separated clock request output signal to the RCC for its kernel clock and its APB clock whenever the device is in run, sleep, or stop mode. 2 interrupt lines are connected to the NVIC: error interrupt line and event interrupt line. The 4 FIFOs can be programmed to generate DMA requests when they need to be serviced. This slide and the next one illustrate the overall programming sequence of the I3C peripheral when acting as primary controller. After reset, the I3C peripheral is in the default disabled state. In this state, the software has to execute the sequence described in this figure prior to enabling the I3C peripheral. The 3 initialization steps are detailed: initialize the I3C bus and select controller operation, configure the management of all targets, and configure the execution mode of a frame and target requested transfer. Then, when software writes 1 into the controller-enabled bit of the I3C CFGR register, the I3C peripheral takes into account the value of the different configuration registers and switches to the enabled and idle state. Once the I3C controller is in idle state, it's able to initiate a frame transfer or concurrently receive a start request and/or a target-initiated transfer, hot join, or controller role request from an allowed target. In the first case, the I3C peripheral switches to the active state and executes the frame transfer on the I3C bus until the completion of the last messages, unless a transfer error is signaled. See the left part of the active state box in the figure. The software is notified by the corresponding event and/or interrupt, and the I3C switches back to idle state, where it may be reconfigured for a next frame transfer. In case of target-initiated transfer, the hardware receives and logs the request from the target in its registers, and an event is generated to notify the software on the completion of the frame or on a detected error. This slide and the next one illustrate the overall programming sequence of the I3C peripheral when acting as target. When target is in disabled state, the software performs the following initializations: set I3C peripheral as target, set I3C bus timings, configure target-initiated requests, initialize target characteristics and capabilities, configure the execution mode of a transfer, and configure interrupt generation or polling mode from any event. Then, the software can enable the I3C peripheral. The following target-initiated requests are supported: inbound interrupt, controller role request, hot join request. When the target is in idle state, the target is ready to receive a communication message on the I3C bus from the controller and is ready to switch to the active state. All substates of the active state are represented in the bottom part of the figure. From left to right, the various communication messages that are handled by the target are inbound interrupt, controller role request, hot join, receipt of a write broadcast CCC, receipt of a direct read or write CCC, receipt of private read or write request. Common Command Codes, or CCCs, are I3C's standardized commands. A broadcast write CCC is seen by all I3C slaves. A direct read or write CCC may alternatively read or write data from or to one or more specific I3C slaves, one slave at a time, selected by the slave dynamic address. A private read or write is a memory-mapped access to a register in the target. Back in idle state, the software may update the configuration of the I3C target before a next transfer. Refer to the upper left part of the idle state description. This table lists all supported broadcast CCCs. Depending on the particular CCC format, a subcommand byte and data bytes may be provided by the controller. Number of data bytes is indicated between parentheses. The ENEC and DISEC CCCs allow the controller to control when target-initiated traffic is allowed versus is not allowed on the L3C bus. Dynamic addressing is required by the I3C protocol while supporting static addressing for legacy I2C devices. As an optional feature, multiple I3C target devices can share a single group address, allowing a controller device to send a given L3C message to all target devices in the group at once rather than one at a time. The following CCCs are related to addressing: RSTDAA, ENDAA, SET-A-ASA, DEF-GRPA, RST-GRPA. The ENTA-S0 to 3 CCCs allow the active controller to inform one or all target devices that it will not be active on the I3C bus for an approximated amount of time, so that the target devices may use a lower power state during that period. The DEF-TGTS CCC tells secondary controller devices what targets and groups are present on the I3C bus via 4 consecutive data bytes per target or group. The SetMWL and SetMRL CCCs allow the I3C controller to set the maximum data write length and respectively maximum read length for all target devices. The STM CCC informs all I3C devices that the controller is entering a specified test mode during manufacturing or device tests. The SetXTime CCC provides the framework for controllers and targets to exchange event timing information for purposes such as synchronizing controls, collecting or reconstructing timestamps, and specifying the timing data procedure. The RST-ACT CCC is used to configure the next target reset action. This slide and the next one list all supported direct CCCs. The ones that can also be transported through a broadcast CCC have been explained in the previous slide. The SetD-ASA allows the controller to assign a dynamic address to one target using the target's static address. This is faster than the ENT-DAA dynamic address assignment procedure. The SetD-ASA CCC should be used before the ENT-DAA CCC is used. All targets without assigned dynamic addresses will respond to the NDAA CCC. The SetNewDA allows the I3C controller to assign a new dynamic address to one I3C target or secondary controller. The GetMWL and GetMRL CCCs allow the I3C controller to get the maximum data write and respectively maximum read length in bytes for one target device. The GetPID CCC is a GET request for one I3C target device to return its 48-bit provisioned ID to the controller. This unique ID is used by the dynamic address assignment procedure. The GetBCR and GetDCR CCC are a GET request for one I3C target device to return its bus characteristics register, or BCR, respectively device characteristics register, or DCR, to the controller. The GetStatus CCC is a GET request for one I3C target device to return its current status to the controller. The status information includes activity mode, error status, and pending interrupt status. The GetACCR CCC is used both to verify a controller role request, if received earlier, and to allow the active controller to offer or to pass the controller role to an I3C secondary controller, even if it was not previously requested. The controller uses the GetMXDS to determine the SDR mode data speed limitations of one target device. The GetCaps CCC allows the controller to query an I3C target to determine what optional I3C features that target supports. The D2DX CCC initiates and controls the device-to-devices tunneling procedure. The SetXTime CCC provides the framework for controllers and targets to exchange event timing information for purposes such as synchronizing controls, collecting or reconstructing timestamps, and specifying the timing data procedure. The GetXTime CCC provides the framework for the controller to query the exchange timing capabilities supported by the I3C targets. This figure illustrates the I3C broadcast NDAA CCC as it's communicated on the I3C bus and as it's programmed when acting as controller. After NDAA is presented, followed by start or repeated start with the reserved byte, the knowledge is driven from the address targets. The target then sends its 48-bit unique and provisioned ID in open drain, which is subject to arbitration. The target which wins arbitration then continues, providing its BCR and DCR. The controller transfers the 7-bit dynamic address for the winning device in open drain plus parity bit. If parity bit is OK, the target shall acknowledge. The procedure is iterated until the controller detects a NAC condition after having transferred the reserved byte. This means that all targets have been assigned a dynamic address. Note that the figure mentions the registers for the I3C peripheral that the controller's software has to access during the sequence. This figure illustrates the I3C broadcast NDAA-CCC as it's communicated on the I3C bus and as it's programmed when acting as target. The assigned address is captured in the I3C dev R0 register. Here's the format of the provisioned ID. Bits 47 to 33 of the 48-bit provisioned ID is 15-bit STMicroelectronics MIPI ID 0x0104. Bit 32 of the 48-bit provisioned ID equals 0. Bits 31 to 16 of the provisioned ID equals 0. Bits 15 to 12 of the 48-bit provisioned ID equals MIPI ID field of the I3C EP IDR register. This MIPI ID field is written by software to set and identify individually each instance of this I3C IP with a unique number on a single I3C bus. This figure illustrates the I3C direct CCC write transfer except RST ACT as it's communicated on the I3C bus and as it's programmed when acting as controller. The controller first issues the I3C reserved byte with RNW set to 0. Once properly acknowledged, the controller transmits the CCC code and subsequent optional bytes if CCC defines byte, subcommand byte, and data bytes. As mend equals 0, this message is followed by a repeated start before another message is to be emitted. In the second message, the controller transmits the target address followed by n bytes. When mend equals 1, this message from controller ends with a stop, being the last message of a frame. This figure illustrates an I3C private write transfer as it's communicated on the I3C bus and as it's programmed when acting as controller. The M-type field of the control register selects the message type, binary 00010 for private message. This private write transfer can be scheduled when one of the following conditions is satisfied. An arbitrable header containing the reserved byte and RNW equals 0 is emitted after a start and before the I3C private write message. The target address is emitted directly after a start. The I3C write message follows a previous I2C or private I3C transfer. The controller selects the target by transferring its address and indication of a write data transfer direction. Then, data bytes are sent by the controller, separated by transition bit. The transfer ends with a stop or repeated start condition. Configuration fields that have to be initialized by the controller, address of the target, direction of the data transfer, number of bytes to be transferred. The status register is updated with the control word message ID programmed in the control register to which the status information refers, the direction of the transfer, and the number of transmitted data bytes. This figure illustrates an I3C private read transfer as it's communicated on the I3C bus and as it's programmed when acting as controller. This private read transfer can be scheduled when one of the following conditions is satisfied. An arbitrable header containing the reserved byte and RNW equals 0 is emitted after a start and before the I3C private read message. The target address is emitted directly after a start. The I3C read message follows a previous I2C or private I3C transfer. The controller selects the target by transferring its address and indication of a read data transfer direction. Then data bytes are sent by the target, separated by transition bit. The transfer ends with a stop or repeated start condition. Configuration fields that have to be initialized by the controller, address of the target, direction of the data transfer, number of bytes to be received. The status register is updated with the control word message ID programmed in the control register to which the status information refers, the direction of the transfer, the number of transmitted data bytes, and an abort flag is set in case of early completion from the target. This figure illustrates an I3C private write transfer as it's communicated on the I3C bus and as it's programmed when acting as target. Each target compares the target address with its assigned address. DA-val bit set indicates that dynamic address is valid. When a match occurs, the target acknowledges the request and prepares to receive data bytes. The frame complete flag, or FCF, is asserted by hardware to indicate that a message addressed to this target has been normally completed on the I3C bus, for example, when a next stop or repeated start is then issued by the controller. The status register is updated with the direction of the transfer and the number of received bytes. This figure illustrates an I3C private read transfer as it's communicated on the I3C bus and as it's programmed when acting as target. Each target compares the target address with its assigned address. When a match occurs, the target acknowledges the request and prepares to transmit data bytes. The frame complete flag, or FCF, is asserted by hardware to indicate that a message addressed to this target has been normally completed on the I3C bus, for example, when a next stop or repeated start is then issued by the controller. The status register is updated with the direction of the transfer and the number of transmitted bytes. Bytes to be transmitted may have been preloaded into the TX FIFO. This figure illustrates IBI, in-band interrupt, transfer as it's communicated on the I3C bus and as it's programmed when acting as target. IBI is enabled when IBI EN bit is set to 1 and the target was assigned a dynamic address, which is confirmed by DA-val bit set to 1. In the upper right part of the figure, the IBI is masked due to either the IBI target event disabling or dynamic address resetting. In order to request an interrupt, an I3C slave shall emit its address into the arbitrated address header following a start but not following a repeated start. If no start is forthcoming within the bus available condition, then the I3C slave may issue a start by pulling the SDA line low and then wait for the current master to pull the SCL low. If the current master sets the SCL line low, thus completing the start, and then provides clocks on the SCL line, then the slave shall drive the SDA line with its own address, followed by an RNW bit with value 1. If more than one slave has issued an IBI request after the same start, then the current master shall process those IBIs in priority level order. This arbitration loss case corresponds to the arrow right to left from NAC condition back to the beginning of the sequence. The slave that lost the arbitration may issue another IBI request, but shall not do so until after the bus available condition. The slave which has won the arbitration transfers mandatory and optional payload bytes, as represented in the bottom part of the figure. These bytes identify the cause of the interrupt request. This figure illustrates IBI, in-band interrupt transfer, as it's communicated on the I3C bus and as it's programmed when received as controller. The address of the target that has won the arbitration is captured into the Received Message Register, or RMR. The IBIF flag is asserted by hardware to indicate that an IBI request has been received. This flag is cleared when software writes 1 into that bit to indicate that the current IBI has been handled. When an IBI is received and the previous one is not yet handled by the controller, this second IBI is ignored. The I3C IBI-DR register is used to receive the IBI data payload, and IBI-RDCNT field logs the number of data bytes effectively received in the I3C IBI-DR register. The software should initialize the C-FIFO management to be then written either directly by the software or by the allocated DMA channel. As soon as the transfer is initiated, a transition to active state occurs. When a DMA channel is used, the DMA automatically writes control words into the I3CCR from its memory source buffer until the frame completes. Software management is based on the C-FIFO not full flag, CFN-FF. Software C-FIFO refill can be based on polling or interrupt. Polling mode waits for a next control word is requested by the hardware, which is indicated by the CFN-FF flag set to 1 before an explicit write to the I3CCR register. When interrupt mode is chosen, an interrupt is requested when the CFN-FF flag is set to 1 by the hardware. The message continues until either an error occurs or it's the last of the frame. The DMA mode for the C-FIFO management can be modified when the I3C peripheral is not in active state. If a transfer error occurs, then the C-FIFO is automatically flushed by the hardware. If C-FIFO is empty and a restart has to be emitted with a new control word, a C-FIFO underrun is reported. The software should initialize the TX-FIFO management through the following programmable settings: enabling and disabling DMA mode for TX-FIFO, configuring TX-FIFO threshold, enabling and disabling TX-FIFO preload, enabling and disabling interrupt. The threshold defines when the TX-FIFO not full flag TXF NFF flag is set. When threshold control bit is equal to 0, 1 byte threshold TXF-NFF is set when 1 byte is to be written in TX-FIFO through the I3C TDR register. When threshold control bit is equal to 1, one-word threshold TXF-NFF is set when 1 word is to be written in TX-FIFO through the I3C TDWR register. As soon as the transfer is initiated, a transition to active state occurs. When a DMA channel is used, the DMA automatically writes data words to the I3C TDR or I3C TDWR register from its memory source buffer until the frame completes. Software TX-FIFO refill can be based on polling or interrupt. The configuration for the TX-FIFO management can be modified when the I3C peripheral is not in active state. If a transfer error occurs, then the TX-FIFO is automatically flushed by the hardware. If TX-FIFO is empty and a data byte has to be transmitted on the I3C bus, a TX-FIFO underrun is reported. The table in this slide and the next one lists all interrupt sources present in the I3C peripheral. All event interrupt sources are ORed together and reported to the NVIC by using the I3C EVTIT line. All error interrupt sources are ORed together and reported to the NVIC by using the I3C ERRIT line. Refer to the reference manual for the complete list of error types. Each interrupt source can be individually masked or enabled. The 4 events at the beginning of the table can be used as DMA requests to inform the DMA that data has to be transferred between memory and I3C peripherals FIFOs. Events in this slide are related to the I3C peripheral acting as a target. Most of them correspond to the receipt of a particular CCC. In addition, completion of an IBI, a reset pattern detection, and a misstart are signaled. When entering stop, the vCore domain is supplied. By default, any clock oscillator is disabled, and in any case, neither the system clock nor a peripheral clock is running in the vCore domain. A controller can wake up on an IBI without MDB, a hot join request, or a controller role request. A target can wake up on a target reset pattern or on a missed start, as explained in more details in the next slides. When the peripheral acts as controller before the product enters a low-power mode, the software must issue an ENT ASX CCC, generally with x equals 0, 1, 2, or 3, to inform targets that the I3C controller is not expected to exit from idle state, neither to communicate on the I3C bus before an interval of, respectively, 1 microsecond, 100 microseconds, 2 milliseconds, or 50 milliseconds has elapsed. This delay defines the TCAS delay for the controller to set the SCL bus clock low and running after a start condition. More specifically for a stop mode, the CCC must be restricted to an ENT ASX with the value x equals 1, 2, or 3. The I3C peripheral is able to wake up the system from stop mode. This is only possible when SVO-S3 is selected before entering stop mode. This slide describes the wake-up sequence when the I3C peripheral acts as a controller. First step, the I3C peripheral requests its kernel clock to the system. On a detected start condition on the I3C bus, SDA line is detected to be driven low while SCL is high. As controller, as initiated by an external I3C target device for a hot join inbound interrupt controller role request. Second step, The system enables the source oscillator of the I3C kernel clock, and the clock gets ready after a few microseconds from HSI. The user may keep the source oscillator on in stop mode to reduce the startup latency at the expense of power consumption. Once the kernel clock is provided and running, the I3C hardware uses an internal timer to wait for the corresponding TCAS time to elapse, then drives low SCL and continues toggling SCL to let the target perform its hot join, in-band interrupt, or controller role request on the L3C bus. The I3C peripheral maintains the kernel clock request until the generation of the stop condition on the I3C bus. Third step. As controller, the I3C peripheral requests its APB clock to the system on the ACK address of a received IBI request, and it maintains the APB clock request until that IBIF is cleared. If the IBI is without MDB, a stop is normally generated on the I3C bus, even if the APB clock is not yet provided. On the ACK address of a received controller role request, and it maintains the APB clock request until that CRF is cleared. On the ACK address of a hot join request, and it maintains the APB clock request until that HJF is cleared. Fourth step. The system is notified of the I3C APB clock request, and the power management unit of the PWR module is awakened. Fifth step. An additional delay may be needed for the regulator if it must increase the voltage for run mode. Sixth step. The system enables the system clock that drives the APB clock. There's an additional delay if the selected oscillator source for the system and APB clocks is not the same as the one driving the I3C kernel clock. If so, the system enables the source oscillator of the system clock, which gets ready after a delay. Seventh step. With the APB clock running, the peripheral can log the I3C transfer in its status and data registers. When the bus transfer is completed, the peripheral generates the corresponding flag IBIF, CRF, or HJF, and the enabled interrupt can wake up the CPU. The target reset pattern is a specific scheme for a controller to wake up and possibly reset a target from a low-power mode. It consists both in the RST ACT CCC and in the in-band reset pattern generation. As target, the sequence for the I3C wake-up from stop on a reset pattern is the following. First step, when the peripheral detects a reset pattern on the bus, i.e. 14 SDA transitions, while SCL is kept low, it requests its APB clock to the system to set the RSTF flag of the L3C EVR register. Second step, the system is notified of the I3C APB clock request, and the power management unit of the PWR module is awakened after a few microseconds. Third step, an additional delay may be needed for the regulator if it must increase the voltage for run mode. Fourth step, the system enables the source oscillator of the system clock, which gets ready after a few microseconds. Fifth step, with the APB clock running, the I3C peripheral can raise the RSTF flag of the I3C EVR register, and the enabled interrupt can wake up the CPU. As target, the wake-up sequence on a missed start is the following. First step, the peripheral requests its kernel clock to the system. On a detected start condition on the I3C bus, SDA line is detected to be driven low while SCL is high. As target, as initiated by an external I3C device, either controller or target. If the kernel clock is not provided before that SCL is driven low by the external controller, then the I3C target detects that an I3C bus start is missed and waits for the kernel clock to be provided. It can be noted that an I3C controller message intended to be addressed to it may have been missed and nacked, or may have been missed any I3C CCC or private message from the controller to another addressed target or an in-band interrupt, controller role request, hot join start request from another target. Second step, the system enables the source oscillator of the I3C kernel clock, and the clock gets ready after a few microseconds if HSI is the clock source. The user may keep the source oscillator on in stop mode to reduce the startup latency at the expense of power consumption, especially if the controller is in an active state of x = 0, with 1 microsecond TCAS latency. Third step. After that, the kernel clock is running as target. The I3C peripheral requests its APB clock to the system to raise the WKPF flag conditioned by non-user text. Or, fourth step, the system is notified of the I3C APB clock request, and the power management unit of the PWR module is awakened after a few microseconds. Fifth step, an additional delay may be needed for the regulator if it must increase the voltage for run mode. Sixth step, the system enables the system clock, which drives the APB clock. There's an additional delay if the selected oscillator source for the system and APB clocks is not the same as the one driving the I3C kernel clock. If so, the system enables the source oscillator of the system clock, which gets ready after a few microseconds. Seventh step, with the APB clock running, the missed start flag, WKPF, of the I3C EVR register is raised, conditioned by non-user text. If it occurred, and the enabled interrupt can wake up the CPU, it's then known that an I3C bus transaction was missed, but not whether the target was addressed or not. The software should use a timeout in order to return to stop mode if it's not addressed by the controller again within this interval. Refer to the application note AN5879 that provides some I3C examples based on the STM32Cube-MX to cover most of the I3C communication modes available on the STM32 microcontrollers and to provide recommendations for the correct use of the I3C peripheral. In addition to this presentation, you can refer to the following presentations: Reset and Clock Control, Nested Vectored Interrupt Controller, General Purpose Direct Memory Access Controller, and Power Management.